This laptop next time. All right, so thank you for coming today. I'm sorry for the delay. For some reason, Zoom stuck somewhere. Hi, how are you? So, computer architecture and computer organization. What we covered last week. Why is the computer, what we call the computer is a large digital circuit. And what's the reason behind that? Why we say it's a large digital circuit? Because we know we'll use combinational circuit and sequential circuit. And we went over how to do a design for combinational circuit by using which method? Came out, correct? And what else we covered last week? We discussed, the computer, how the computer look like. And we said the computer is divided to multiple components. And this component is one of them is CPU, memory, and disk. That's really the major component. There's of course other. And we discussed about the CPU, and we said the CPU divided to two components. The first one, which is called controller, and the other one is the data path, ALU part of the data path. So data path is divided to, what do we call it? The building blocks. So that's what we need to do the operation. For example, what the component usually we have in the data path? ALU, one of them, correct? Registers. What about MUX? What about buses, correct? So all of these together, we build the data path. And the controller is work as the brain of the computer. It's control everything, when you have to do this operation, when you have to fetch the command, when you have to run it, when you have to store the data to the memory. I don't know why it's keep asking me to admit you guys, but next time I'll try to change this option. Guys, over Zoom, can you hear me?
Yes, sir.
Okay, good. Perfect. So that's what we covered last week. Okay, and we discussed how we do a symbol design for 2-bit adder. And we use the K-map, correct? So now let's go to today class, and we'll do a quick review, same thing for the K-map again, but let me open that. Do you have any question from last week? Is there any question? Any easy, hard question for me? Nothing? That means I did a good job. So, okay. So today I will use the one note because it's easier for me to, can you see, correct? We need to make it bigger for you. I have to change my screen resolution. Actually, I'll leave it like this. Because if you make it smaller, it's going to be hard for me to write. All right, so why we said the computer is a large digital circuit? Because we will use combinational circuit and sequential. And we said we'll cover the combinational circuits and we'll do some designs. And we will see how we can to reach our goal. What's our goal in this course? To build a computer. And so we will go over the combinational circuit, digital design. However, we will fit that in our course. We'll explain digital design, but we will tweak it toward our course, not just digital design. We'll learn digital design, then apply that to this course. So, and for combination circuit, what we said, how many methods we can use to do a design using for the combination circuit. We said there is a limitation. So we say we can use K-map if the number of input less than or equal 6. Why? What's the reason? because if you remember, yes. So what is the size, or how many K-map table we need for a design? So the K-map or number of tables we need, it's equal number of output. So that's not an issue. Usually our output is not too many, but it's tables, so you can divide your problem to tables. The problem when your input it's more than 6. Why? Because our table size will be 2 to the power n. If this n it's bigger, it's more than 6, like let's say 8. What is the total number of cell we need? 120 or 265? Sorry, 250, 260, 256, correct? Can you do a K-map for a cell as 256? It's going to be complicated. That's why we said, if it's up to 6, okay, it's hard, still hard to do a table for what's the 2 power 6? 64. So still, it's hard, but it can be done. It's going to take some time to build a K-map. So that's why we said if we cannot, I don't know why, guys. Can you see admit button somewhere? Waiting room here. Where's the security button? Top. Left. Okay. Enable T. Okay. Let's see. I don't know. I think when I set up the meeting, I did not remove this option. All right. So if we cannot use K-map, what do we have to use? Correct. Bit slice approach, and we'll see today how we can use that. And if we cannot use the bit slice approach, there is another way, correct? So today we will go over the K-map again, just a quick review, and what's the K-map meaning for the K-map, why we need a K-map, and what's the purpose of the K-map, and we will make it more clear today. So last time was, we did the K-map last time, but we did not really understand why the K-map, why we need the K-map. So what we will do here. So what is the purpose of the K-map? Is to reduce the logic. So if you have a circuit, the purpose of that to reduce it by eliminating or keeping the common, and we'll see with example. So that's the whole idea of the K-map. So for example, let me delete that. I'm not a tech savvy. I'm trying, because we have a student joined by Zoom, so that's why I'm using technology. So for example, if we have this equation, F equal A B or A B bar. All right. So how we can reduce this equation? So what we can do, what we will do, we will see the common and we'll take them. So what is the common here? So A in both sides. So what we'll do, we'll take A out. We'll leave B or B bar, right? So what is the B or B bar? It's 1. If it's 1, always 1. If it's A1 or 0, it's gonna be the result's gonna be 1. So then the result, what will the result will be? A. So what we did in this case? So in this case, we eliminated the different logic, and we kept only the common. So the common here A, and we eliminated the different logic. That's the reason why we did the sequence 0, 0 here. 0, 1, 1, 1, and 1, 0. Why is not 0, 0, 0, 1, 1, 0? Because that's 2, then 3. What's the purpose of that? Why we did this way? Why we did that? The reason you're trying to change only one bit at a time. So 0, 0 changed to 0, 1. That means how many digits changed? Only one, correct? This one changed. All right, now if you want to move from here to here, so you have 0, 1, what's changed? Only the 1 here, correct? So the changing only one bit. Now, if we do the opposite, if I change this one to, if I change this one to 1, 0 here, what that mean? I'm changing both of them. 0, it's 1 now. I'm sorry, 0 become 1 and the 1 becomes 0. So I'm changing two bits next to each other. So when I try to reduce the size by combining or try to combine these two together, that's mean both of them will be eliminated. We cannot use the common. We cannot keep the common. So we cannot combine them together. Correct? So that's really the reason why it went from 0, 0, 0, 1, 1, 1, then 1, 0. That's the reason. So now let's take another example. Let's delete that. So we have another example really to reduce, which really simple. Now this one, I'm not going to write it because it's really simple. So what's common and what is the common? Okay, what is the common? What is the common here? So you have A, B, C bar, D, E, and you have A, B, C bar, D bar, E. What we have? So okay, that's the common. A, B is the same, C bar is the same, and E is the same. What's the difference? It's only the D bar, I'm sorry, the D here and the D bar here. So how you combine them? By just put the common out and then D and D bar together. And what's the result? Only A, B, C bar, E. So in this case, what we did, we eliminated the difference. The difference here is the E, because E bar, it's cancel each other. It's going to be 1. So, and that's why we did that. So now, let's go to this table. And in the K-map, remember, we try to combine the ones by 2, like 2 together or 4 together or 8 together, right? So now, how I want to combine these two? Correct? So now, how we can write this equation? So if we have 1, 1 and everything 0 now here, what's the equation for this one? So remember, that's, I'm sorry, here's C, A, B, and C. So you will keep the common. So now, so A, you have, that's A is 0 and A here is 1. That's different. So we don't need that. We cannot take it. So what is the common? It's the B, B1, and the other B here is 1 because I'm looking just only for this two. I'm looking only for this two now. So in this case, what I have to do, I will keep, so I will say output or equal. I will keep the A since it's A1 on both sides. And what I will do, I looked up. I looked this way. Perfect. Now what I have to do, I have to look this way now. Perfect. So what is the common here? Because it's in the same row, is not changing. It's always 0. So what's I will have here? It's going to be C bar because it's 0. Let me repeat that. That's digital design. But let me repeat that. So usually, again, when you have ones, you try to combine them. Combine them either in 2s or 4s or 8s or 16. So based on the table. But since we have small table, so we have only 2. And how you write the equation? Let's see. So out equal, I will look this direction first. And what is the common? 1 and 1. And that's 1 and 1. It's represent the B because it's AB and AB here, correct? So A change it from 0 to 1. So we'll not take, we'll ignore. B, because it's B, it's 1 and stay 1. That means it's common. I will write it here. I need it. And I wrote down it's B, not B bar. Why? Because the value is 1. Perfect. And if you take this side, what we have? You take this side. C is the common, which is 0. So it's going to be C bar. So now that's how you reduce the equation. So what that means? The K-map is just kind of they call it graphical, show or telling you how to reduce the circuit using the K-map. So that's really the purpose of the K-map, is to reduce the logic. So that's our answer, correct? So K-map is simply a graphical implementation of logical adjacency theory. Okay, so the theory is, when you have two logic next to each other, not changing, then we keep them. If they're changing, we can eliminate them. Okay, that's the theory, really. All right. So now, as we mentioned before, is there any questions so far? It's a simple K-map here. So when you have 16 cells, it's going to be more complicated. And we will go over some examples. Clear? So in the exam, if I ask you what's the purpose of the K-map, to reduce the logical equation, simple. By eliminating the keeping the common, correct? By removing the difference. All right, so as we said, if the input is less than or equal 6, we can use the K-map. If it's more than that, we have two options. Either we use a slice approach, and we'll do an example now, or you can use a heuristic approach, and we'll see that later. That's going to be more advanced, but we'll see. All right, so last week we explained the two-bit adder, correct? Let me see if I can. So I want to refresh your memory. So what we said, if you want to add A and B, and this one is, 1001. All right. So what's the result will be? It's gonna be. Let me just change the battery very quick. I think it's this way. Just make sure we are safe. Okay. All right. So if you want to add A and B, how you add that? 0 plus 1. It's 1. And 1. What's that carry? No carry, correct? But now what is the extreme here? When you add 1, 1 plus 1, 1, correct? And what's the result will be? Number 6, correct? 3, that's equal 3, correct? And that's equal 3. So it's going to be 0, 0, 1. So we'll have the carry. So don't tell me it's low on battery, this one. So if you have two inputs, and this one 2-bit, and this one 2-bit, and this B, and that's A, what's the output will be? 2 or 3? It's going to be 3, correct? Because you will have the carry here. All right, and that's how you design it now. And if you want to change the representation, either you can do this one, or you can do 4 input, and you name it B3, B2, B1, and B0, and you will have again 4 input A3, A2, A1, A0, and you will have you can do some 0 and some 2, correct? So now, what's the K-map for that? I'm not gonna finish it because that's part of the assignment. So, but I'm trying to refresh your memory. How many tables we need? The table, it's equal the number of outputs. So you need 3 tables. And what's the size of each table? Yeah, I'm sorry. We're trying to do 2 bits, so I want to remove this 2. Correct? So we need 2 bits. So what's the size of each cell? 2 to power 4 equal 16. So how's the tables gonna look like? Maybe 4, so and 16, and this one is gonna be A0, A1, and B0, B1. Correct? So that's the K-map. So we did that last week. Just I'm trying to refresh your memory. So now if I go back here, so as we said, it's gonna look like this. You will have 3 tables. One table for C out 0, C out 1, and C out 2. And each table has 16 cells. And how we can, so after we decide the size of the table and the number of tables, what's the next step? To fill out the table. So just we'll do because some of you maybe missed it last week, or so let's say I want to fill out this cell. So what this one? It's 1 1, sorry, 1 1 plus 1 1. What's the result? 0 0 1, correct? So what you will do there, we'll do 0 0 1. All right. So we'll take another one. If you want to take this one, what's the result? 0 plus 0. So it's going to be 0 0 0. So you will fill out the whole table with the numbers. Then after that, what's the next step? To do the reduction by combining the ones in group of 2 or a group of 4 or a group of 8 or a group of 16. All right. So for example, I want to do an example. That's not really right, but it's, after you fill out the table, you will get a result like this, 1 1 1. So how you will combine them? You combine them like this, correct? And then you write the equation. So let's say, you have zoom in. Trying to zoom in, but does not work, but that's fine. So let's say let's do different ones and see how we can combine the stuff. If I do 1, okay, 1 1 1, I have 1 and 1 here, then I will do 1 and 1 here. How we combine these ones together? Remember, we have to try to combine them in 2s. If you combine them bigger, it's better, of course. But if you cannot, there is no way to combine them in 16 or 8, then you try the 4, then you try 2, all right? Then finally, if there is no way to combine them, then you have to leave them alone, all right? So for example, what I can do, can I combine this 4 together? Perfect. Now, what about this 2? Can't do that. What about this one? Correct. So I combine this one with this one. All right. So now, in this case, I reduce the equation, Now, sometime you got to the point, there is no way to combine. I'm trying to find one for you. Even if you have 1 here, what you can do, still, if you see this one, we're already combined, but still, we can use it to help this one. You can combine that. Sometime you stuck, let's say, you have 1 here, then you have zeros around this guy. So what you have to do, if you have 1 here, then I have zeros. There's no, this one is going to be, leave it alone. We cannot do anything with that. So that's the K-map. If you still have a problem with the K-map, it's really easy. Just go review it very quick. Because assignment 1, it will be this is the adder. Just you have to finish it. You have to write the equation. It's a really simple assignment. But I'm not trying to finish it for you guys. I give you at least for now. All right, so that's the adder. Now, the question for you. Can we extend that to 4-bit adder? Yes, we can do that, correct? We can. But the question now, we cannot. Why? You have 8 input, correct? It's more, it's going to be complicated. So you will not be able to do it. Now, the question for you, how we can fix this issue? How we can do a design for bit pattern? So we have to use different approach. The K-map is not going to work with us. So in this case, what we'll use second approach, which is called bit slice approach. So what that's mean, you divide your problem to 1-bit problem, and you do a design for only 1 bit. Then somehow you combine the 4-bit together to build the whole, circuit. Okay. So as we mentioned, we need 5 K-maps because we have 5 outputs, and we need 2 to the power 8, which is really hard in the K-map. So out of picture. So what we can do, we try to find an approach, and the approach is how we usually do the add. You do it by hand, correct? So that's an example here. So for example, if you want to add these 2 numbers, so that's for 4 bits, correct? But as I told you, we'll deal with it as 1-bit issue. So what I will do, I'm looking at these 2 bits and how you add them. Usually when you want to add A and B, usually sometime you will have a carry. You will have a carry from the previous stage, and you will have carry out going to the next stage, correct? So for example, I'm adding 0 and 1, and there is 1 before and 1 after, assuming that. So what is the result here? I will have a carry. Let's assume it's 1. So what's the answer will be? It will be 0 and 1. So you have a carry out, all right? So in this case, what's your circuit going to look like? If you think about it, okay, your circuit is going to be something like, I have A of I going in, and you will have B of I. So you will have this one, A of I. And we name it A of I based on the stage. So if it's stage 0 or stage 1, we say A of 1 or A or B of 1. So at stage I, that's your input, and that's your, you will have input. Now, what else you will have? You will have carry, correct? From where? From a previous. So how we will write that? We'll say carry minus 1 from the previous, right? And that's your input, correct? What's your output? What's your output will be? You will have sum I, because that's the stage I, and what you will else you have? Carry I, correct? So that's how it's gonna look like in the circuit. So that's only 1 bit. So now we have to do design for that. Perfect. So if you look at here, you will have, the CI minus 1, that's the carry from the previous stage. And you will have BI, AI, and sum of I, and you will have the carry I. And if you want to do numbers here, again, if you have 0, 1, and the previous stage give you 0, the sum will be 1, the carry will be 0. If you have 1, 1, and the previous is 0, so it's going to be the output is going to be 0. Well, I'm sorry, 1, and the carry 1. So you are dealing with each stage as a separate problem. So we slice our problem to multiple or n bits approach, and we will do design for only the 1 bit. Then after you do the design for 1 bit, then you can replicate that. If you want to do 4-bit adder, so what you do, you replicate this circuit 4 times, then somehow we connect it together. We'll see how we'll connect the links together. All right. Is there any questions so far? Now let's do design for this circuit. It's really simple circuit. All right. How many inputs we have? Correct. 3 inputs. What's the size of the table? I'm sorry, 8. Because it's 2 equal 2 power 3. 8. So 8 cell table. How many tables we need? We need 2 because we'll have 2 outputs. So how that's going to look like? Let me clean that for you. So I have it down, but I'm trying to not go ahead, try to explain it to you. So how it's going to look like the eight cell table? It's going to be like this. And what I will write here, A of I, B of I, correct? And what we'll have here, C of I, or C of I minus 1. Perfect. So that's the table. How that, and that's one, this table for what? For the sum of I. Then you will have another table. Trying not to show you. I have another table because I need your answer. And it's going to be the same thing. Remember, you will have 0, 0, 0, 1, 1, 1, 1, 0, correct? And we'll have 0 and 1. Same thing here. We'll have A of I, B of I, C of I minus 1. And it will have it 0, 0, 0, 1, 1, 1, 1, 0. You have 0 and 1. And that will be for carry I. Now let's, what we have to do now? Next step, throw numbers. Perfect. So let's throw numbers here together. Okay, so the first one is for the sum. Let's assume I'm trying, so what I have, the first one, I'm adding 0, 0, 0. Sorry. I'm adding 0, 0. That's A, that A of I, B of I, that's carry of I minus 1. Correct? So in this block, what's the A of I? 0. B of I, 0. And the carry, 0. So what's the result will be 0. Now let's take this cell. What I'm trying to add? I'm trying to add 0, 1, 0. What's the result? 1. That's for the sum. What's the carry? That's the sum. What's the carry? 0. So we'll have here 1, and it will have here 0. Perfect. Let's take another example. Let's take this table, this one. This cell. What we have here? You will have, you're trying to add 1 plus 1 plus 1, correct? You will have 1, 1. You have 1, 1, and 1. So what's the result? 3 is 1 and 1. So that's the sum, and that's the carry. So what you will do, you will do 1 for the sum and 1 for the carry. All right? Do you need me to go over the whole table, or it's really easy? Easy, correct? So let's give you try another cell. I'm trying to put this value here. And this 2 cell. What's the numbers I have? What's some numbers I'm trying to add? 1, 0, 1. What's the result? 0, 1, correct? So then you will have 0 and you will have 1 here. All right. So that's really simple. Let me delete that for you. By the way, last week I did not share the screen in Zoom. That's why the recording was only my voice without any screen. So this week I shared it. Now it's recording with my sharing. So I will upload it to YouTube in case if you have to review it. All right. So now that's our table. We got 0, 1, 1. I'm sorry. So we did 0, 1, 0, 1, 1, 0, 1, 0. Now let's combine the ones together. Can we combine any ones and 2s or 4s or 8s? We cannot, So that's why we have, when we write the equation, it's going to be separate for each one of them. Now for the carry, we've been able to do this 2 together, this 2 together, and this 2 together. All right. So based on that, when you see 4, that means you will have or. So you will have 1, 2, 3, and 4. Correct? We have 4 and with the 3 ors. Okay. Now we'll write the circuit. And here, how many you have? You will have 1, 2, and 3. What that means? You will have something like this. That's the circuit. How it's going to look. Now, let's just try to write it and together, and correct me if I made any mistakes. Maybe we can, okay, let's clean that. Maybe we can write it here. So I want to write the circuit of the sum of I. Let's take this one. Can you give me what this one? You have to remove the common, or not the common. So because it's only one, it's you circuit only alone. That means you will have the 3 variable included there. So you will have AI bar, BI bar, then CI minus 1, correct? That's the first one. Or let's take this one. What we will have? AI bar, BI, then C minus 1 bar, correct? Now let's take this one. Now both ones, so it's going to be AI, BI, then the CI minus 1, all of them ones. Then the last one, which is, it's going to be AI, BI bar, and CI minus 1 bar, correct? So that's the equation, how the equation is going to look like. All right. So now, okay, so that's what we did here. All right. So in the digital design, if you have function like this, I needed to correct. If you have something I bar, B, or I of I, B of I bar, so the opposite each other. Can you tell me what this circuit? This one XOR. All right. So that's in digital design. So if it's meaning, your output will be 1. Okay, if one of the input is 1. So for example, you have A equal 1. What that's mean? So this one, it will be A equal 1. That will be 0. I'm sorry. A equal 1, that's 1. And if 0, B will be 1. So the result will be, if 1, 1, the result will be 1. If you do the opposite, that's A, I'm sorry, that's A and that's B. So if the opposite is 0, 1, what that's mean? This one will give you 1. And this one will give you 0. So when you OR 1 with 0, the result will be 1. So when you OR anything with 1, the result will be 1. When you AND anything with 0, the result will be 0. So that's why the XOR, one of them has to be 1. If both of them 1s or both of them 0s, the result will be 0. The only case the output will be 1 if one of the input is 1 and the other 0. That's what they call XOR. Oh, and that's why if you look here, if you look to this circuit, so if AI, BI, and CI minus 1, and that, if you see this one, okay, do we have another AI, BI bar? Let's see. Maybe here it's easier. AI, BI, CI minus 1. And it's mostly so the two together, it will generate the circuit, but we don't have to worry about that. So at the end, that's the result. It's going to be AI XOR. Okay, I wrote it XOR because I could not find the sign. It's hard to find it, so I did XOR, but that's really the sign. And it's BI XOR C of I minus 1, of course. So that's the circuit for the sum. Correct? Now let's do the carry. Clear here? Is there any question? again, when you do the design, you can write your circuit using this equation. But when you do that, when you build a design, you will have too many ands and ors, and it's going to cost you more of that gate. So when you transfer it to XOR, you're saving in the hardware. However, lately, when you will see, sometime you have to expand the circuit for a reason, and we'll discuss it now. So either you expand your equation, okay, or you combine it. So the purpose here, when we did the XOR, we saved some hardware. It's less gates. How many gates we have here? 2 XORs, correct? And if you see this equation, how many no, you will have 4 ORs. And how many ANDs? You have 1, 2, 3. I'm sorry, 3 ORs and 4 AND gates. All right. So you have total of 7 gates. Here you will have only 3 gates. So you're saving money and the hardware, but you're slowing the speed, and we'll see how. All right. So now let's go to the carry. The equation for carry should be easier and shorter. All right. So let's take this first 2 here. Can you write this one for me? This 2, I'm looking for this 2 together. What is the common? It's the BI, correct? And it's 1 because it's 1, 1. Okay, and when you go this side, it's CI minus 1, correct? We'll do OR. Let's take this 2. What will have this 2? I'm looking for this 2 column here. What is the common? AI, correct? AI is the common. And if we look to this line, CI minus 1, perfect. Then OR this one here, sorry, this one. What's the equation for that? 1, 1, because I'm taking the whole column. So it's going to be AI, BI, and can we take the CI there? No, because now CI, if you see, change is not common. So that's the equation. So how many ANDs and ORs? 2 ORs and 3 ANDs, and it's only 2-bit input. So now what's how the circuit's going to look like here when you draw it? So you will have the OR, and that's the F, for example, or that's the carry. Let's say the carry. Then what you will have here? You will have and you will have another and, correct? You will have 2 input. And what is the first input if you want to write it? It's going to be AI, BI. Second one, it's going to be BIC I minus 1. The last one is going to be, I think there is 1 bar. I think maybe this one is bar. I'm sorry, BI bar. That's the C. So the first one, AI, BI. Second one, it's BI, CI minus 1. And the last one is correct. The last one is going to be AI, CI minus 1. So that's how the circuit's going to look like. All right, don't worry about it because we will draw it again. Now, the question for you. Can we change this one? Can we group it in a different way to help us with the size of the circuit? Usually we do what we do usually. We combine them by 2s or 4s or 8s. Now, for the benefit of reducing or reusing some of the gates, can we change this grouping somehow? Yes. So If I change that, if I do the grouping similar to this way, so what's the equation will be? If I do the grouping here, so let's take the first one. I'm sorry, let's take this one. So let's do grouping for this one. What we will have here? It's gonna be I, BI, correct? Or now let's take this one. What we will have? It will be AI bar, correct? BI, CI minus 1, or, correct? What we will have, it's gonna be AI, BI bar, CI minus 1, all right? Now let's take these two together here somehow. Let's combine them together. What is the common? We'll take CI out, correct? So how we will write this one? We'll say AI, BI first, or we'll take the CI minus 1 out, and then I will leave AI bar, BI, or AI. Yes, oh, good. All right, or BI bar. Can you tell me what this one? Correct. So this one is AI XOR BI. Perfect. So what is the final result? It's gonna look like this. What that's mean? When you convert it to XOR, is that gonna help us? Is that gonna help us since we have the XOR somewhere here? Correct? In this case, what I can do, I can build an XOR and I can use it in the sum and in the carry. So again, that's it's come with a try. They have to think how we can reduce the cost and the hardware. And of course, they came with this idea. Okay, now let me not combine and group them by twos. Let me keep them as XOR. And that's what we got. Why? It's going to save you cost of the hardware. Now you can use the current XOR, which you will use for sum, to use it in the carry. So how we can draw the circuit now? All right, so let me draw that here first, without looking for the circuit we have there, because I needed to help me out. All right, so let's do the sum first. Okay, the sum. That's the equation for the sum, right? So how many XORs we need? 2. And we needed 2 levels because we have to wait. So what you do, you will do an XOR. That's how it's going to look like, correct? So you will do an XOR for AI with BI. Then the output, it's going to go to another. I think I'm doing something wrong, but let me see. We'll tell you what's the wrong. Okay. Usually you draw it like this. All right. Then you add another XOR, and that will give you the sum of I, correct? And what you will have here, CI minus 1. All right. That's the circuit of the sum. First you XOR A and B, AI and BI, you XOR them together. Then the result you XOR it with the CI. That's how it's going to look like. Now let's do the carry. How the carry look like? So first you have to AND. You have to AND A and B. So what you can do, you will do an AND here, and you will have A and B, and that's the AND, correct? Then this one will go to and OR. So that's OR, perfect. Okay, and you OR it with what? You will add it with the result from the AI XOR. So from here, not from the sum, because we need it only from AI BI, correct? I'm doing XOR for AI and BI, not from here. So I have to take it from here. And you AND it first with CI minus 1, which is this one, correct? And this one goes here now. And that will be carry I. All right? Clear? If you have a question, stop me, guys. You know, we can repeat it. You know, we have the whole day. You know? So, okay, how it's gonna circuit is gonna look like? So first XOR, and then the second XOR, that's for the sum, that's the output here. Then, as we said, you know, we have an OR, and you AND AI with CI minus 1, and the result from the first XOR with the CI minus 1, right? And then finally, when you do the box like this, that's how the circuit is gonna look like, right? That's only one bit now, correct? So now how you can build four bits adder from this one? So it's really easy. What we can do in this case, just repeat it. And how we will repeat it? So let's say, you know, you design, that's the first one bit. You will have A of 0, B of 0. Let's make it another bit. So that's what we did so far. We did this design. So that's the sum of 0. That's A of 0, B of 0, and that's CI minus 1. Now, initially, CI minus 1, it's 0, right? Because we don't have carry. So, and how you give 0 in digital design, you just ground it. That's a ground. All right, that will give you 0 here. Okay, so that's only one slice, correct? Now, if you need 4 bits, what you will do, you will repeat the same design. You already did it once. You don't have to do the design again. You already have it. So, and just put the input. What you will have here, A1, B1 as input, then A2, B2 as input, then A3 and B3 as input. Perfect. What else we have? We need carry, correct? And usually the carry coming from the previous stage. So what we'll have, and that's C0. So this one will come as input here. And what we will have output here, sum of 1, and it will have carry of 1. And this one is going to go to the next stage. Same thing, you will have sum of 2, carry of 2. So we'll go back here, carry of 2. And finally, we'll have sum of 3 and carry 3. All right? So how many stages we have here? 4, correct? So now, using one slice design, you focus on only one slice. You build it. You did your best to make it, fast. Then we just replicate that and design. Now, can I create 8-bit adder from here? So what we have to do to create 4 8-bit adders? Add 4 more and connect them. Just move the carry. All right. So that's how we usually do a manual, like by hand, how you add. You add the numbers. If there is carry, you add it to the next stage. Then you do the second stage number 2. You add them. If there is carry from the previous stage, you add it. And then if there is carry, you add it to the third stage. So you do stage by stage. Now the question, let's discuss the speed of that. All right. So what's the speed will be for that? So usually, let's do timing very quick. That's our timing. Let's that's your input A, and you have B. Okay, let's say A start with 1, then goes to zeros. So, and let's B start with, let's say stay ones. Okay. So now, what's the result will be? I'm sorry. And you will have the sum, and you will have the carry, correct? And let's say initially the sum, the carry from the previous stage is 0, all right? So let's work here. Let's say now you have 1 here, right? 1 plus 1, it's going to be 1, 1, it's going to be 0, 1, correct? The result? So it's going to be 0, okay? And this one will be 1. All right. Now at this point, what's going to happen? Will be the result? Now, when A goes to 0 and B stay 1, the output will be 1 and the carry will be 0. So the sum should go to 1 and the carry should go to 0. All right. However, in the digital design, always there is a delay. So which is mean here at this stage is not going to change right away. It's going to take slight delay, then change. Same thing here. It's going to take slight delay and change. So always you will have a delay here. And that's part of the digital design. That's how's the gate. Always there is a delay. Now, when they start doing a design, this delay maybe used to be 5 nanoseconds, right? And the computer was slow. Then with the time, they've been able to improve that, for example, to 0.02 nanosecond, right? In the future, maybe they will enhance that, and maybe they can reduce this delay to maybe 0.1 picosecond, for example. So for us, we should not worry about the speed or the delay. We should use a term, and this term will represent the delay. And in digital design, we use something called delta. Okay. So when we talk about delay, we talk about how much delta it's the gate will delay. So you don't have to worry now what's the technology we have now, if it's slow or fast. You just represent it by delta. So we say, this gate is going to take delta time, delay or speed to do the operation or to translate to the next stage, right? So now we're not going to mention anything about numbers. We say, delta. So delta equal delay. Now currently, let's say, it's 0.2 nanosecond. In the future, maybe it's going to be picosecond. So we will talk about the delay. So now let's see the circuit and see how much the delay. So in digital design, usually, so let's say each gate, each level, it takes delta delay to get the result. All right. So that's what I assume. Each gate is going to take a delta. Now, in this circuit, okay, how much delay we will have until we receive the sum? The sum, through how many gates is the sum goes through? No, the sum, only the sum one. The sum. So it's gonna go, remember the sum is gonna go through this gate, then it's go through this gate, correct? So how much the delay for the sum? It's 2 delta. Now, how much the sum for the carry? 4, 3, 4. Who said 4? 5, 4. Who said 3? Answer is 3. Why? Because remember, this one, it's in the same level as this one. You can't do the and. You're not waiting on anything. So the carry is going to come through this gate, all right, and this gate, then this gate. So it's a 3 delta. Overall, so now for the 1 bit delay, how much? It's a 3 delta. Now that's only for one slide. Now let's discuss that on the 4. We draw it, I'm sorry, here, correct? So 4. How many? What is the total delay for 4 bit? 12. 9. Who said 9? 9. 12. 12. The answer is a 12. Why? Because you will have here up to here, that's a 3 delta, correct? Then you have to wait. You cannot start here. Of course, it's going to do addition because that's, remember, that's combinational circuit. So keep doing results, but you got the right result. Okay, you have to wait for this carry. It's going to go here. Then it's going to take another 3 delta here, 3 delta. Then finally, you will have a 3 delta to have everything. So the total will have a 12 delta. All right. So now let's go back to, that's 12 delta, correct? Now, if we are doing only 2 bits, what is the delta delay? 6, correct? Okay, 6 delta. Now, if the fast adder, which we used the K-map when we did the first design, when we did the circuit. So what's the delta? What's the delay? If you remember, we went here. Okay, this one. What is the delay? It will be 3 delta, correct? So now we've been able to this one is still fast, correct? However, we cannot use it for 4-bit adder. We cannot use it for 8-bit adder. So still slow. You know, the delay will be, we said 12 delta. Still slow. Can we improve that? Can we improve it before the break or after the break? Yeah, let's take it, guys. 10 minutes. And after we come back. Now let's say, what's the problem here? Now, if you think about this one, what's the problem in this design? What is really holding us from the speed? The carry. So is there a way to break this line? To break it and get the result faster? Is there a way? Yes, there is a way. And we'll see that after the break. All right. Okay, guys, we'll take a break and come back. Let me stop sharing. I'm sorry, stop recording and come.